I want to introduce a colleague, a dear colleague of mine. And so let me share a little bit of a story behind the scene. So he also worked in search ads quality along with my team. We worked together. And there's this one time that he and I had a chat. He said, I think we've built a pretty good system in search ads quality. And I think we should build this system to make more Google teams that can use the AI system we want. I'm like, yeah, sure, go ahead. So he went off and worked with some other person. His name happened to be Jeff Dean. So a few years later, this is sort of a toy system, right? They started to building this toy system and eventually launched. The system is called TensorFlow. So let's welcome the co-founder and Eng director of TensorFlow, Rajat Monga.
Thank you, Yunkai. Thanks. Thanks for that great introduction. It was fun working with Yunkai back then, and it's still fun to see you all here doing all this amazing stuff. So, today I wanted to talk a bit about the revolution in machine learning that's been happening over the last few years, and it's really picking pace, now. So let's take a look at what's happening. Deep learning, which is a branch of machine learning that's really been behind us. If you see this graph, just shows the interest in that area over time, based on Google Trends data. And as you can see, starting back in 2014 or so, it's really picked up. Our team, Google Brain, was founded around 2011, and it was still very, very early days back then, but it's really done very well since then. This is an interesting picture that I love to show. One of my colleagues, Dave Patterson, who's also a Turing Award winner now, so really amazing colleague, who basically we have these archive papers, so people write all these ML papers, and there's a place you can put them on archive. This sort of shows the growth rate for machine learning papers over the last few years, and it really matches what Moore's law was doing. Even though Moore's law itself is kind of dead, but this is pretty amazing to see that doubling every couple of years. So what's deep learning? Here's a very simplified picture of what deep learning is. You have, if you're doing for vision, then you take a picture, pass it through a number of layers, and each layer, it's sort of activating some neurons or turning them on, passing those inputs up, keeps going up, makes a prediction. In this case, says cat or dog. Maybe it predicts cat or dog in this case, and then if it's right, great. If it's wrong, then it actually tells the layers below what's wrong and why is it wrong, and sort of trains this all. And this entire thing is called a deep neural network. So let's take a look at many of the different fields that it's really having an impact in. And there's lots of different things it's doing. One of the most interesting things to me is healthcare. Healthcare is important to all of us in many different ways. And while that wasn't an area that we started with, we are starting to see lots of impact in that. One of the interesting areas is pathology. And in this case, you see pictures taken off a pathology slide. And then using a network that we just saw something like that basically applied to these images. And interestingly, it gets really amazing scores on trying to figure out where the tumor is. On the right, it sort of shows that on the red. In this case, the algorithm has actually done better than trained pathologists significantly. Another area the same thing's been applied to is diabetic retinopathy, and some of you might have seen this before. So we have this picture of the back of the eye, which is called a fundal image. And there's a disease called diabetic retinopathy that occurs in lots of humans, some hundreds of millions of humans in the world. And if diagnosed correctly early on, it can be fixed very easily, but if not, it can lead to blindness. And again, in this case, the algorithm does better than the median ophthalmologist. It can be trained over tons and tons of pictures. Most ophthalmologists can only look at so many pictures over their lifetime. What's interesting about this is it doesn't stop there. So that's where we started. And here's an interesting story about this one. So for this group, a new person joined the group, and Lily, who was in charge of this group, said, okay, why don't we try predicting something else? We've been doing great predicting the problem for diabetic retinopathy. Can we predict something else? And why don't you just go and try if you can predict gender from this? And the expectation was, you know what, how can this really predict gender? So let's just try it out. It'll just teach this person what we can do with that. Then that person came back and in a few days, and they got an AOC score of 0.7. The average, if there's no correlation, is like 0.5. And Lily was like, that doesn't seem right. You should go and check all the data. And then a day or two later, the person comes back again, and the score is like 0.85. So like, wow, there's something in there. And then the team started looking at many different things on how it scores. As you can see with gender, there's a very high chance of predicting gender just based on these images, but also many of these other things as well, like your systolic and diastolic blood pressures and so on. It isn't as good as the invasive procedures yet, but again, you can do this just by taking a picture without drawing blood and so on. So it's really interesting biomarker that could change how we do things. In healthcare, one of the interesting areas has been, can you actually predict what's going to happen to a patient? And there's lots of work that's gone on in this over the last many years. More recently, I think it's more interesting for a number of reasons. One, the electronic medical records data that's really grown over the last 10 years, and over 95% of the patients in the US, I believe, have electronic medical records. So can we actually apply techniques like what we've done with translation and natural language processing to this as well? Turns out, you have all this data for patients that's de-identified and all these different records. And our team was working with lots of different healthcare organizations, including some ones listed below. So can we make predictions around these different things that you want about a patient? And why is this happening? Turns out you can, and these new techniques can actually do way better than what was happening before. In fact, as much as 24 hours before what the earlier techniques were doing. So the baseline was the dotted line. As you can see, it's trying to predict, make a prediction about this is what's going to happen to this patient and so on. And now we can do that at least 24 hours earlier, which really gives the doctors a chance to make a difference in these patients' lives. Another area we can do this is, okay, healthcare is great. Can we actually do better medicine itself? So can we engineer better medicine based on using machine learning, using deep learning in these? Here's something that's been done for years. For building medicine, you basically put together some molecules, and you try to predict properties of those molecules. So there are ways. There's this density functional theory-based simulators that takes something like 20 minutes to figure out for a given molecule if it's going to be toxic, if it has certain properties, whether binding with proteins or not. So that's great. That's been used very, very effectively over the last few years. But can we do better than that? So it turns out there's a certain kind of neural network called message passing neural network that was built a couple of years ago. And it can do a similar job, basically looking at that and making a prediction in 1/100th of a second, and really making the same kind of predictions, and in fact getting better predictions as well. So not only is it faster, something like 10 to the 5th faster, 300,000 times faster, but it's also better. And this was done last year, and these are the kind of changes that will help us get way more better medicine, and much faster as well. One of the biggest things about medicine is trying out all these possible molecules, and this really makes that whole process faster. One interesting thing for all of us has been, we have brain which we don't really understand how it works. Can we, again, apply machine learning, deep learning, which is inspired by some of the ideas in the brain itself? Some people say it's really how the brain works. We don't really know how the brain works, but it definitely hasn't been inspired by ideas there. So can we learn more about the brain in turn to improve deep learning itself, or many other things too? Turns out we can. So there's this whole idea of connectomics, where you take an entire brain, you slice it up, and try and figure out all the different neurons and connections in that brain. And the thing on the right at the bottom that you see is a picture of a slice with the dots, etc., that you sort of see, and you want to connect it into all these different wires. So there's been a lot of progress in that. We started way at the bottom there in 2015. And in this case, the expected run length is basically how long can you connect a neuron or an axon really without having an error, right? And if you see in terms of the run length, primates are way on the top right. And we are still pretty far away from that, but we're getting pretty close to what's a songbird, which is 100 micrometer sort of scale to get a slice. And let's take a look at what's happened there to make this possible. So this particular paper, basically what it did was, instead of it took a 2D slice that you start from, and then start with some random point, make a prediction about that, and use something called recursive neural networks to really keep making predictions. As you can see, it's making great progress on trying to identify the entire region, and over time kind of does that. It's still very computationally intensive, but it does a really good job of identifying the right thing. And in fact, you can take that and you can do this across a 3D space as well. So in this case, you see, again, a neuron for a songbird being filled in. This is at something like 60x the real-time rate, so it's really, really slow. There's still lots to speed up there. But it still, it has the potential to let us really map the entire songbird. And here's examples of some of, how some of those look after you've mapped them out, et cetera. So in this case, the raw data was produced by the Max Planck Institute for neurobiology, and overall we have these 600 billion voxels that we want to map completely, and it seems like it's doable. There are lots of other changes that are happening that we believe will speed this up as well. Another area that's very exciting to us is robotics, and who wouldn't want robots going around the house helping doing things. For example, doing the dishes for me, or just cleaning things around behind my kids, I guess. So lots of interesting things that robots could be helping us with. So this is something we did a couple of years ago, where we had an ARM farm, basically, with about 10 of these robots. And there's a camera that you see at the top right of each of those robots. It's basically taking a picture and trying to identify different things and learning to grasp just automatically, right, by making mistakes and doing all of that. So this was still very early work. Since then, there's been other work, in this case by DeepMind, where these robots in simulation are learning to walk. And when they start out, they have no idea what to do, right? But they can literally learn to avoid all kinds of objects in the middle, go under them, go over them as well. And in this case, go around objects as well. And there's one more fun one. So the interesting thing about all of these is they started with really no understanding of the world at all, and they learned by basically making mistakes, using some deep learning models and something called reinforcement learning. So these are some great research ideas, right? But beyond this, beyond our labs, beyond our research labs, lots of people are taking these and applying them to all kinds of different disciplines. So let's take a look at a few of those disciplines and how people are using this as well. One exciting thing is, our universe is huge, and there are lots of planets and solar systems out there. One researcher, in this case, happened to be a Googler in our lab itself, who had an interest in astronomy as well, but no background in astronomy, decided to take some of this data and really use machine learning, use deep learning to identify new planets in the Kepler solar system. And it basically found this system which is very similar to our solar system. That's basically the only system that we know of that has 8 planets very much like our solar system outside our own. And this was an interesting discovery that was aided by deep learning. This interesting one is for farmers. There's a company called Connectera over in Netherlands that's basically put these tags on cows and senses what they're doing, how they're doing, takes charge of what their health is, etc. And basically guides them through, make sure these are healthy. So making really sure that the cows in these farms remain healthy as well, applying machine learning to those sensors, data, etc. that's coming through as well. This one's very interesting. So there's climate change. A lot of us do believe that science itself has a big role to play in fighting climate change as well. And in this case, deforestation. So some people took these tools, collected data about sounds of saws and tree cutting, etc., and trained models to identify when something like this is happening, and deployed these models in the forests to really identify if there's any kind of deforestation happening and so on, to prevent these kind of things happening, really helping fight climate change as well. Art is not beyond this as well. In this case, this is something called NSynth, where deep learning and generative models really help artists build better music or build different kinds of music. They explore different kinds of music along with artists and allow them to, it's sort of like a jamming session with another artist and playing with interesting things. And finally, lots of products from Google itself. Pretty much every product we make has machine learning somehow behind the scenes. Like on the Pixel 2, when you take a picture in portrait mode, it actually uses machine learning to identify what's in the foreground, like what's the human and what's behind, and sort of does the right thing. In case of Clip, it identifies when to take a picture itself. In case of Assistant, of course, there are many different parts where you use machine learning, including voice recognition to the assistance itself. And pretty much across the board, every single product that we build uses machine learning in many different ways. So what's changed? Machine learning has been around for a while. Like Yunkai said, he's been doing this for a very long time. So what's really changed now? So back in the 80s, 90s, there were all of these approaches to machine learning, and neural networks was still there. In fact, it's been there since the 40s, in the early 40s. But the accuracy wasn't quite there. But since then, we've really added compute, where we can shift the scale from where it was back in the 80s, 90s to here. And neural networks are starting to do better than pretty much every single approach that you see out there for lots of different areas. So what's really enabled this? Of course, it's more compute, but there are also tools that you need. So one of the important tools that I'm very excited about, of course, is TensorFlow. That's really enabled all the different things that you saw just now in my presentation. And this was released in the open source about 2 years ago. We've had lots of launches since then. And we've seen the popularity keep going up over the last 2 years, and it continues to go up. There's still, in fact, we have over 11 million downloads for TensorFlow since it was launched. So really, lots of change happening, and it's not just in research groups, as you saw with some of the examples. People are using it for all kinds of things as well. I love this slide because this sort of shows where people are doing this. And as you can see, there's some interesting stuff happening all the way north in the Arctic Circle in Tromsø, Norway, to the bottom really at Deception Island, which is in Antarctica, so going all the way north to south, and in fact east to west as well. Across every single time zone in the world, there are people using TensorFlow and doing machine learning with it. So what can you do with these tools and machine learning? One of the important things today for machine learning is to get a solution, you need all of the combination of these. You need expertise, you need data, you need computation. Now, each of these is hard to get. Can we make improvements in some of these? So can we, in one case, take data and more computation and cut down the expertise that's needed? And that's something that we've done recently. So there's this idea of neural architecture search to find a model where you have a controller that really predicts a model that can make a change, that predicts what a kind of model that would work for your problem, evaluates that, trains that, evaluates that, and does this for many different models, basically, and then looks at which one's the best, and in this case, shows up with something that's really, really accurate, and sort of keeps going until it finds a good one. It also does some crazy things. So it builds this kind of a model, which probably no human would do because it doesn't really have any structure, kind of looks pretty random, but it gets pretty amazing results, and that's fine because we don't necessarily need the model to look pretty. We want something that works in this case. So the interesting thing is, so here you see these different models that have been built over the last few years, and each of these took years to actually build by researchers over lots of years, starting from inception to exception more recently, and different. And each of them has different computational needs, each of them has different accuracy and so on, and people use many different ones of these. So and if you see this red line, these are all the models that were built using AutoML, or learning to learn as we call it, neural architecture search approach that we have. And as you can see, it's really outperforming all these handcrafted models. And if you look at the top, it's building these models not just to be higher accuracy, but also using less flops, so they're less computationally expensive. And at the bottom, the same kind of thing, where it's giving you more accuracy for the same kind of flops when you're deploying this on the phone or doing on some device. You really care about that as well. In fact, this is launched as a service on cloud for Vision right now, so you can automatically train your models in Google Cloud. So they're very encouraging signs that we can take these models and build something amazing, really flexible systems that can solve new kinds of problems automatically. But as what we saw, it needs 100x more compute. As we saw, we already needed a lot of compute. Now we need even more. So can we do something better for those? Turns out for deep learning, you have very special computation properties. We often use floating point numbers, which are 32-bit, lots of precision. Turns out you really don't need that kind of precision, and you can cut that down. So reduced precision is fine. And in fact, turns out that a small number of operations, in this case matrix multiplies or convolutions, are the ones that use the most compute. So given that we know that, can we do something better? And turns out we can. So last year at Google I/O, we announced the TPU, V2 of Google TPU, which is Google Cloud TPU. It has 180 teraflops of computation with 64 gigs of memory. And in fact, it's designed to be connected together, so you can really build an entire supercomputer with them. This supercomputer is basically 11.5 petaflops, targeted towards deep learning, really focused on that, and makes it possible for us to do some of the research that we're doing today. Again, this is something that's available in Google Cloud as well. People are using this and getting some amazing results with that too. So you saw all these different things that we've been doing with deep learning, all of these different applications that we've been doing, and amazing results that we're getting. And we believe that there's lots more that can be done by using deep learning, by using the tools that we have. So we would love to encourage you to try this out too. And we believe that it's really important for deep learning and machine learning to be used in every single product that you do to build. Thank you.